And with that, we start also the live stream now, and I welcome you all back to the workshop again. It's day 6. We have a slight change of plans with Simon's lecture starting right now, and we'll do that. We start also the live stream now. We will do the reflections and project developments right after that. So with that, I'll give it away to Simon Bechert. He's a structural engineer from ITKE, the institute led by Jan Knippers, Professor Jan Knippers. The ICT is collaborating since now more than 10 years. And yeah, there's an exciting presentation ahead with a bit more the focus on the engineering of some of the projects that we did together. And Simon was working as one of the lead engineers. With that, I guess, Simon, if I forgot anything to introduce, no, that's a chance where you can stand, I guess. And I'll give it away to you.
Okay. So hello, everyone. My name is Simon Bechert. I mean, as Jakob mentioned, I work at the Institute of Building Structures and Structural Design for Professor Jan Knippers. Jakob and I have worked together on the Buga project, the Buga Wood Pavilion, which I will present today. And I will also present another project, the Urbach Tower, which you can maybe see here. I don't know if you've seen it before. It's a quite artsy, kind of landmark that was made from curved CLT. And I'll just share my screen and start. If you have any questions, feel free to ask. I mean, Jakob and Hua made me aware that you will post your questions in the chat. Please interrupt me as often as you like. Just gonna share my screen now. And if you don't understand something, or if you want me to go back, feel free to hop in. I'm just gonna activate the chat again. Okay. All right. So the topic of my talk today is anyway, I'm gonna look at these other screens, so it's just seen from the side. I hope that doesn't bother you. Is integrated design and robotic fabrication of lightweight timber structures. So we're at the ITPE. We're mainly structural engineers. We also have some architects in our team. I called it the topic of my talk. Also, I included robotic fabrication, even though it's the main part that ICT is taking care of for our projects. And also the projects that we develop are always a collaboration between the two institutes. Okay, so I would try to set the frame for my talk. I would try to give you a general insight of the work at our institutes and how we approach the design and construction of lightweight timber structures, and also why we think that our work, or that this work, could be in somewhat relevant for future construction, even though they're, of course, on the side of teaching and research. Okay, so as we all know, there has been a drastic increase of population since the 1960s, right? So from 3 billion people to more than 7.5 billion people. So what looks like here, like a linear increase, is actually very exponential when you go further back in time. So over the last 57 years, the global population has grown by 4.5 billion people. To put this in perspective, I chose Shanghai as an example. So every year, the world is growing by approximately 86 million people per year. And the largest Shanghai has a population of 24.3 million. So this means approximately 3.5 times the largest city of Shanghai is growing per year, or the people, the inhabitants, are growing per year over the world. And of course, you have to know that Shanghai is a very, very large city. So if I did this talk in Europe again, and it was, I think, 5 times the Netherlands. So if you compare it to countries, it's even more impressive, I would say, than comparing to a city. But as I'm doing this work, or having participating here now in your workshop, I thought Shanghai would be a nice example. So in the early 2000s, more urban population there was more urban population than rural population. But in 2007, the urban population actually surpassed the rural population. So what does that mean? In developed countries, over 90% of the population lives in cities. And this, of course, has some sort of effect on cities, but how exactly? So one good example, or one very prominent example, is the urban sprawl of Phoenix in Arizona, in the United States of America. So how does, so the city, the boundary of the city has grown over the last 30 years by a huge amount. And as you can see in the white dotted line, and this means that more area is also needed, and the city becomes even more, even denser, right? But this also happens in other part of the country, of the world. So these mega cities emerge. One good example is Tokyo in Japan, with almost 10 million or around 10 million inhabitants in the city center, and even more in the larger part of the city. And another good example is Mumbai, where 50 million people inhabiting the city center. What it also means that there's a clash of different social classes with different housing standards. So you as architects and engineers have also to accommodate for that, right? So you have to address these social differences. So according to the United States Global Status Report, one major challenge will be to provide building floor area in the construction industry. So this means basically we have to build more floor area.
Welcome back, everyone.
So in yellow, I'm sure
for day 3
might also have
of our workshop.
Shown this to you before, but I'm just gonna repeat it. And so in yellow, you can see the existing building floor.
We have an exciting guest lecture today
by 230 billion
Uwe,
square meters. So this existing building floor area needs almost to be doubled in the next
coming up
30
in
years.
around 1 hour. Before that, we thought we go again through the project briefing.
For new building or for new buildings on the floor area is not only limited to
giving
Asia
you
and Africa. It's also
a bit of a better understanding of
like
what
Europe
we think
North America,
we would like to guide you through until Friday.
To grow by more than 50% over the next 30 years.
And
to put this in
then we should also see how the teams are coming up.
Okay. So this basically means
sure
that the entire world needs to be built again.
If you, I guess you all have access now, right?
To put this in numbers, it means that it requires 65,000 square meters.
I cannot see any signed up groups yet, so we can form them.
And this translates to an area of 250, like the 65,000 square meters are translating to an area of 255 by 255 meters, or 9 soccer fields.
But I guess before that we can go through a bit of
so the current challenge in general here,
maybe a bit of a repetition of what we already discussed, but I think it's really important to get that
building for more leads also
and,
to other certain consequences.
So
we as the building industry consume a fair share of the global energy. So the building and construction sector consume more than 35% of the global final energy. From an analogical perspective, this means that this energy consumption means also more CO2 emission. So there has been a constant increase of CO2 emission since industrialization. And over the last 50 years, these emissions have also increased by almost by a factor of 4 to 35 million kilotons. Which is why in 1992 the Kyoto Protocol was established during the United Nations conference.
The problem or the challenge that we address in this workshop is the limitations of timber construction at the current moment. Right? This is not to say that the current developments in timber constructions are not super exciting and also
so it becomes quite obvious
very much advanced. I think we saw in the last couple of presentations, and you're going to see that even more in the upcoming presentations, that timber construction can easily be called one of the most digitally advanced construction sectors, right? But there's still a lot of things to tackle. And one of the challenges
40% of energy-related CO2
that we identified is the limitations of the structural column to slab systems that is mostly limited to very clear spans and or short spans, not really performative and materially efficient.
So what could we do
with that? To set the goal of this workshop
to build for more,
with
less
to the collective exploration
less energy consumption.
With all of you guys,
but how is it possible?
To find new spatial, structural, and
one approach that
topological potentials within timber construction,
at the University of
and our hypothesis is that if you bring an on-site mobile robotic fabricator into the game, we can achieve multi-directional and monolithic timber slabs. But really the question
we try to learn
is how can these slabs look like, right? And what can be achieved with timber construction given that technology. I guess we as
in biology,
workshop leaders have a couple of ideas about this, but obviously I think it's way more exciting to get like a lot of opinions and a lot of ideas into the playing ground, right? So I think this is really the summary of what we're trying to achieve with you, right? And I hope this is also really interesting for all of you who are maybe in practice to see like where could timber construction go in the next years, right? What is maybe already almost possible, right?
And also one
stay kind of on the edge of the field.
Characteristic is that
and also for all of you guys who are in academia, maybe this is a good exercise in what we believe is maybe a bit of a structured approach in exploring novel potentials in architecture.
Material efficient, and
as you know, we split the whole workshop in kind of 5 core research areas. We have the boundary definition, which is mostly the creative ideation of what kind of spatial situation you want to address with this timber building system.
I'm showing this here because the 2 projects.
Then we have a computational analysis area where we will show, and this is going to be the focus of today's second session.
So
we're going to show
correlation between
how you can address very complex
geometry
boundary conditions with computational analysis, generate performative networks of beams mostly.
So in architecture,
we will then
curved shells have been a powerful way to
have a focus on the tectonic articulation.
However,
this is similar of what we did on Saturday, but with the aspiration of making this a bit more advanced in terms of really defining the position and the arrangement of all the beams in a way that they both make sense.
Therefore,
and
a variety of alternative strategies have been developed
and are feasible to
produce these double curved structures.
And I guess additionally,
by using linear elements, as you
can discuss the aesthetic qualities, or we can discuss the structural qualities and so forth.
Grid shell.
Then
or by using planar
you have the area of
elements,
fabrication,
you can see on the,
right, where
in the
we
middle and on the
already
right.
introduced you to the mobile fabrication
So
agent.
the one in the middle is the
We're gonna
Exhibition Hall, which was done by
teach you how to simulate specifically that robot on Wednesday, if I'm not mistaken.
I'm quite aware.
And
quite sure you
then we're gonna guide you through kind of like an integrative synthesis
other approaches,
of all these 4 areas,
use discretization
so that you can really put that together into one project that is integrating all of these 4
such as the inside-out pavilion
aspects
in 2019 by the team
in the most
the currently realized switch headquarters, at Swatch headquarters, sorry. And also there are other further novel approaches to reduce extensive form work, with one example being the Nest Hilo from the Block Research Group in 2018. So multiple institutes and companies or construction companies are trying to solve, to create some surface active structures with new methodologies and new approaches. So another solution to tackle this current challenge is to build for more with less, but also to build for more with more timber. So as we're all aware, timber is one of the few building materials that has the ability of storing CO2. So 1 cubic meter of wood can actually store 1 ton of CO2. So comparing to houses having the same level of energy efficiency, a wooden alternative causes approximately 40% less CO2 emissions. And also the amount of atmospheric carbon stored in the timber can be up to 4 times as much as an alternative building material. So this is one good reason why we can see more and more multi-story timber buildings emerging over the last few years. And I'm quite sure that Jakob has shown this. Also, I'm just gonna briefly introduce some of them. So also these new multi-story timber buildings are reaching new heights. For example, the Mossenet in Norway, which is currently being the tallest timber building in the world with 80.4 meters. And I hope this is still the current case. I'm not sure if there's actually already a higher multi-story building, but this could only be the beginning, as further studies on multi-story timber construction aim for up to 85-story buildings reaching heights over 300 meters. So there are already new building or new projects in the pipeline that even try to reach larger heights. So there's a clear trend in timber construction to build higher, demonstrating how we have overcome many challenges and limitations facing timber architecture, and further tackling the challenges of required building floor area over the next decades. So this is why we have at the university the excellence cluster, which Jakob is also part of, which is called the Integrative Computational Design and Construction for Architecture. And I'm quite sure he has talked about this, so I'm going to skip this right away. But where in that we focus on multi-story timber buildings and long span. So at the Institute, we have investigated in natural structures and tried to transfer these principles into architecture and engineering in order to build simple and resource-efficient lightweight structures. A few examples, what you can see here in this kind of shortcutted video is our research pavilion that we developed over the few years, and we hope we can apply these methodologies and approaches also in the construction industry. So if you want to check out these videos, you can also check them out online. I'm on the ISB homepage, and I think you have seen these as well. So, sorry. So this is a brief overview of our buildings that we have developed so far, always in collaboration with the ICD and also with other institutes of different universities around the world, or mainly in Germany though, also with biologists from the University of Tübingen. And two of the latest projects I would like to present to you now are the Buga Wood Pavilion, which you can see on the very bottom here on the screen, and the Urbach Tower, both from 2019. So the Buga Wood Pavilion is a biomimetic pavilion realized for this year's Federal Gardening Exhibition in Heilbronn in Germany. The Buga is, so this gardening show was located in the city of Heilbronn in the south of Germany. It was open for public for the last 6 months and closed at the end of October in 2019. So this was already last year. It feels like yesterday sometimes. So the ICD and our institute were given the opportunity to realize 2 biomimetic pavilions on the Buga campus. Both pavilions are located on the summer island. On the right, you can see the fiber pavilion, and on the left, the wood pavilion, which I will now present a little bit further. So the Buga Wood Pavilion serves as one of the main event and concert venues at the Buga 2019. As mentioned before, this collaborative team effort of the 2 institutes, along with various industry partners and sponsors. So the structure is a segmented timber shell made from 376 wooden cassette elements and reaches a span over 30 meters. The tripod shell consists of ellipsoidal global geometry with a rise of 7.2 meters and an arch and 3 arch-like openings with raised edges along those arches. The first major shell realized in that sense, so the first major segmented timber shell, is the Landesgartenschau exhibition hall from 2014 in Schwäbisch Gmünd in Germany. It is a single-layer segmented timber shell made from 243 geometrically differentiated beech plywood plates, which are connected by finger joints and cross-threaded screws. So both of these wood shells are based on biological principles found in the plate skeletons of sea urchins, which have been studied by our institutes for almost a decade. So the research hereby focuses on the topology of segmentation and the plate arrangement in relation to the finger joint-like connections. So in the course of the Buga wood pavilion, which we have finished or built last year, we ask ourselves, how can we actually increase the structural performance and what spans could potentially be achieved? And further, how could we increase structural performance without using significantly more material? So if we go back in our talk, we have to build for more or maybe have to achieve large spans, but try to build with less. So the solution was the development of a lightweight construction system which allowed to triple the span of the Landesgartenschau exhibition hall while using the same amount of wood material per square meter shell area. The Buga Wood Pavilion builds on the biomimetic principle of using less material by having more form, both on the level of the overall shell as well on the level of its individual segments. So as you can see here, we almost tripled the span with approximately the same amount of weight or same amount of material. So this developed construction system is a hollow cassette system, which enables us to build with minimal material consumption and weight. The cassettes have a structural depth of 16 centimeters and are all planar. The hollow cassette system is built up from 2 thin plates that plank a ring of edge beams on top and bottom, forming large-scale hollow wooden cases with polygonal forms. Both plates and beams are made from laminated veneer lumber from Cato Q, exactly. I hope I'm not repeating Jakob. I don't know, in the early session I didn't follow the workshop, but I'm sorry if I do. So the cassettes are joined using 2 different connection techniques. So the majority of seams are joined using a bolted connection, mainly in the convex areas, which allow for an easy and robust assembly and disassembly, which you can see on the top right in the section. And on the kings along the 3 arch-like openings, a screw connection is used as the bolted connection was hardly applicable due to the steep angle between the adjacent segments, which you can see on the bottom right. So for these openings, the kings, we used a crossing screw because the bolted connection was just not possible. So all cassettes elements are additionally connected by finger joints, which allow for the in-plane shear transfer or the transfer of in-plane shear forces. The bottom plate also includes a large opening, which constitutes a distinctive architectural feature but also provides access to the hidden connection during assembly. So this Buga Pavilion was conceived under the paradigm of co-design, a framework that explores the interrelationship of design, engineering, and fabrication through a continuous computational feedback within an interdisciplinary team. So as this Buga shell is quite complex, the geometry and the associated fabrication process impose all sorts of constraints, which permanently need to be checked during all design phases. The linearity of segments, edge length, and so on have to be checked during designing, construction, and also engineering all the time. So this led to a global building information model done by the ICD, which carries all these informations and allows to easily output them for fabrication, which means that there is a parametric geometric model which contains all the geometry, finger joint, bolt holes, etc. So this informed model processes the necessary information for structural analysis by automatically deriving a structural analysis model from it and evaluating the results all within the same environment. So the shell was investigated, calculating numerous structural iterations, resulting in one final geometry. This structural optimization process led to a shell structure which only deforms by 13 millimeter under the given loads. So very briefly, I'm also gonna show the fabrication process, which Jakob did a wonderful job here. I'm still astonished by how smooth this went. So the fabrication process of the building components is a novel transportable 14-axis robotic timber manufacturing platform, which was developed by the ICD and partner companies. So the hollow cassettes were assembled by the two robots, or by two collaborating robots, but I think I'm going to skip this part because I'm sure Jakob has already shown you this and can explain it much better than I can. So first, these cassettes had to be assembled, and in the second step, the over 17,000 different finger joints are machined into the segments with sub-millimeter accuracy. On average, the assembly time per segment was approximately 8 minutes, while the high precision milling takes another 20 to 40 minutes. So all 376 shell components were prefabricated in the factory. The 3 large opening arches of the shell, which you can see here, were pre-assembled in the factory and brought on site in 6 pieces. So the arch was supported on the foundation and a temporary support in the middle, and the assembly then started from all 3 sides. The prefabricated shell elements were assembled in only 10 working days by a team of 2 craftsmen without the use of usually required extensive scaffolding or formwork for such shells. So you can see here we had some struts to locally support the structure, and the components were lifted in by a normal crane. The installation of the individual cassettes were done from the top due to the assembly direction of the finger joints, and it was a predefined assembly sequence which we also had to check back structurally. So we calculated the individual assembly steps just to make sure that we had enough struts to locally support the structure and that everything would go smoothly. And again, the pieces were fitting to serial nominal tolerance, which also helps the entire stiffness, the global stiffness of the shell tremendously. Here you can see a worker assembling the bolts. Like once the components are placed, the bolts can then be connected through these holes. And yeah, the shell was almost done. So after connecting all the segments with these removable bolts, a layer of EPDM foil was applied to provide the shell from water, so to waterproof it. And an untreated large facade plate or cladding was added at the end. So the shell can be disassembled and reassembled somewhere else again, so it can be reused. This was also something that we also included in the design phase and was actually, yeah, given by the Bundesgartenschau that the shell has to be able to be reassembled somewhere else. So the pavilion achieves a column-free span of close to 30 meters by weighing approximately 40 kilograms per square meters. It showcases the possibility for efficient, economical, ecological, and also expressive wood architecture. And for the Buga 2019, for this gardening show, it actually serves as the main event location at the Buga campus. So there were concerts and talks and so on. Okay, I got some messages here. I don't know if you can see them. Hope they don't disturb. And also, which was a quite nice feature, was the warm and subtle embedment of lighting in the openings, which at night gave a nice ambience to the shell. And here's some impressions. Of course, every engineer or architect has, once he builds a shell, or she or he builds a shell, has to get up there. And I think also Jakob took a few pictures like this. I mean, we're quite exciting during that time. So this is me and my colleague Daniel Sonntag, also from ITP, on top of the shell, almost finished, just to check it if it actually holds up. All right, so this was the Buga Wood Pavilion. I hope it was not too repetitive. Since Jakob was involved in the project as well, I'm sure he also showed some of the images. If you have questions now, or if you want to have some structural questions, you can ask me. If not, I'm just going to show the next and my final project, which is the Urbach Tower, which I also have a model here. I don't know if you've seen this before. So it's this very kind of artsy landmark made from curved cross-laminated timber, and which was also done for this gardening show. So in Germany, we have a lot of gardening shows, also in 2019. So the Remstal Gardening Show, or Remstal Garden Show, is a smaller horticultural gardening show located in the Rems Valley in the south of Germany. So very close by to Stuttgart, where we work and live. So the ICD and our institutes were part of the winners of a national competition, and therefore were given the opportunity to build one of 16 architectural landmarks along this Rems River. So here in the center, you can see Urbach with the tower, and there were 15 other stations accompanying our station, or just in the next village, there was another landmark of other architects and engineers. So the Urbach Tower, again, as the Buga Wood Pavilion, is a collaborative team effort of the two institutes, and also, again, of course, along with other industry partners such as Blumer Lehmann, but also with other institutes like the ETH from Zurich, and so on, as you can see here. So the tower is a surface active timber structure made from 12 curved CLT components, which are actually made from hygroscopically self-shaping wood parts, or from hygroscopically self-shaping timber. The tower is 14-meter high, and serves as a building demonstrator, landmark, and shelter for hikers. The design of such a complex structure again necessitates an integrative design approach that incorporates formal, structural, and fabrication design into this one framework. And here you can see these clear interdependencies of different levels of hierarchy, such as the material design, connection details, and the component design. So this allows for constant and continuous computational feedback within our interdisciplinary team. The material design is based on a novel self-shaping process developed at the ICD and the EMPA of the ETH of Zurich that enables an adaptable production of higher curvature CLT parts with less machinery and reduced formwork. So this shape change is actually only driven by the wood's characteristic shrinking during a decrease of moisture content. So the Urbach Tower utilizes this powerful, naturally occurring deformation to trigger this design self-shaping behavior. So it forms only by drying. Yeah, so I think the video explains it much better now. So one active layer and one passive layer are designed and manufactured in a flat state to form one bilayer component. This bilayer transforms autonomously into this final predicted curve shape during the industry standard technical drying process. So multiple of these bilayers then are then subsequently laminated and locked into the band shape by a cold band locking layer to form large curved CLT components. Each fabrication is simulated and tested in close cooperation with our industry partners to figure out what range of curvature is producible in an efficient and an economic way and within a standardized industrial manufacturing process. We further investigated what curvature range is actually required and what impact the curvature has on the structural behavior. So the higher the curvature, the less deformation and therefore the better structural behavior. Architecturally, this results in the very distinctive form of the tower, which constitutes a truly contemporary architectural expression of a traditional building material, wood, celebrating its innate and natural characteristics. The geometric model of the tower is actually quite simple, and despite the appearance of double curvature. The surface geometry is generated by arranging self-similar cylinders with center lines distributed on a top and a bottom circle, which you can see on the left. So this this cylinder is actually just mainly rotated around the two circles and then intersected. But what is quite interesting here is that these cylinders then are used in geometric design could also simply be used for fabrication, as the components were simply nested on the two half cylinders and on a two half cylinder fabrication planks. So each curved components can then be 5-axis CNC cut from single curved fabrication planks without any surface milling process. So the 12 CLT components were nested and cut from 15-meter long, 90-millimeter thick curved fabrication half-cylinder planks of custom CLT material buildups. The approximate CNC machining time was 90 minutes per component. Our design also made use making use of this integrative design process. The CLT material can be designed with a buildup that favors the primary vertical loading direction. So the material is here optimally tailored for the structural force flow, which you can see here again. Like the fibers are aligned along the main force direction. The tower components are connected by crosswise arranged full threaded screws. So also compared to the Buga, oh, there's a question, I think. Or is it just, oh yeah, sorry, I didn't see that. Is this a question regarding the tower, Hani?
It's about Buga.
Okay. Oh, sorry, I didn't. Sorry, I was.
No, it's okay.
So in this case, I want to know how you design.
You can answer it after your lecture.
Okay. Okay, I get back to it. Okay. Sorry, I didn't see it in time. So here for the tower, we actually used again also as for the Buga for the kings a crosswise arranged full threaded screws with different angles, as you can see here. For the tower, the angle constantly changes along this curved seam, so we had to check each seam if the screws are actually applicable for the connection. So the curved seams in varying angles between the components necessitated also a parametric and adaptive joint implementation. So the angle alpha, which you can see here on the left, varied continuously between a range of 126 to 146 degrees. And to accommodate for this range, the enclosed angle theta within one crossing screw, which you can see on the top right, had to change accordingly. So to gain or to achieve the highest stiffness possible. So for this, we we had to implement also the connection into a parametric model. Okay. So the tower features a total length of connection seams of around 157 meters, resulting in 520 pairs of crossing screws. This joining techniques allows for a very clean, easy, and also a very robust on-site assembly, which you can see here in this picture. So these screws had to be, parts of the tower were prefabricated, where the screws came from actually from the outside, were drilled in from the outside, and these pre-assembled components, which you can see, we'll see later, were then assembled on site, and for these seams we drilled the screws in from the inside, which you can see here on this image. So this was kind of the material design and the joint design, and this then comes together to component design, which integrates the material and the joints, as well as fabrication and assembly constraints. So each component is connected to the next using simple alignment blocks, which you can see here on the right, and crossing screws with where the holes were actually pre-drilled in factory. So as I mentioned before, 3 components were assembled to one assembly group, resulting in this offsite and onsite connections. So these assembly groups could be then mounted on onto a scaffolding system for transport, which was further also used as on-site formwork for the assembly. So actually this guy in the picture, if you want to know it, he's actually quite tall and quite large. So the components are actually, I mean, he seems really small next to them. When I saw this photo, I was actually amazed because I knew him, like we assembled the tower, or I mean, he assembled the tower, so I knew him from the project. So. Yeah, so with a total weight of 4 tons, the 4 prefabricated assembly groups of the tower that could then be loaded onto 2 trucks and transported on site. So they were produced or prefabricated at Blumer Lehmann in Switzerland, and then were driven to the site in Germany, to Urbach, where they were assembled in a single working day by a team of 4 craftsmen without the requirement of extensive scaffolding or formwork. So the tower's load-bearing structure exhibits a thickness of 90 millimeters, so 9 centimeters, while cantilevering over 14 meters. So the total height of the tower is 14 meters, resulting in a span to thickness ratio of approximately 160 to 1. The inherent curvature enables a highly slender and lightweight tower structure of only 38 kilogram per square meter surface area. So the Buga was around 40, 42. The tower was around the same value, so 38 kilogram per square meters. And actually, when we assembled the tower, it looked quite like wobbly. Like, so the individual parts, what you can see on the image, like the assembly groups, they seemed really thin in air and were quite soft, actually, I have to admit. But once the tower was assembled and completed, the entire structure was quite stiff, which was good for us, right, as the engineers. Oh, so there's sound. I don't know if you can hear that. Maybe I just. So this is some images, some short videos, but I think also longer videos have been published by now. So what is quite nice about this project, I mean, it's not a real structure. I mean, it's some sort of a shelter for hikers and more like a landmark to see from afar and maybe then go there and look at it. But what was quite astonishing also for me when I saw it in real life, that like on the outside it had these really sharp edges, and on the inside it was really kind of soft in tectonics, and this video kind of demonstrates this quite nicely. So also for this tower, to protect it from water and the environment, custom-made protective cladding layer consisting of glue-laminated larch wood was added on the outside. And also in order to provide the shelters or the visitors from rain, the tower structure was topped off by a transparent curved polycarbonate roof on the top. So there was actually a roof on top. So I don't think I mean, it should provide shelter. So we added a roof on top, a very thin kind of also bent roof. yeah, here are some of the results. So the tower is 40 meters high. The CLT thing was 9 centimeters, and so on. Okay, and these are some impressions. And what is also quite fascinating, a lot of local bikers and hikers actually go there and visit it and just have a look at it. Some ask weird questions like, what is the use for this? I mean, of course, it's, yeah, when we were there, I always try to answer these questions as nice as possible. It's more like a landmark. It's not a real, I mean, we're aware that it's not like a real building or anything, and you cannot actually go up to the top because the budget just didn't allow it. But currently we're planning one where you then also can go all the way up to the top. Okay, so this was the Urbach Tower. And I hope I still have 1 or 2 minutes. Just want to give you finish up my presentation. So as you're all aware, this is all basically research. I mean, what is quite nice that we can actually also build stuff, because once you realize these projects, you become aware of of everything else that is needed to actually then realize them. So how can we actually transfer these research principles into practice? So segmented shells could be used for long span roofs of structures that cover interior spaces and structures such as malls or airports. I mean, that is what we imagine. So the example you see here is the competition of the Expo 2020 in Dubai for the Baden-Württemberg house, where we won second prize. Unfortunately, we didn't win, but second prize was also quite nice to win. But yeah, this was our competition design. So it's a segmented timber shell which serves as an enclosure for the multi-story and functional building. I mean, kind of like the Candela shells you see. I mean, they're usually just a long span roof that has then some interior inside. And for the self-shaping wood, we could think of alternative building systems that are as performative as state-of-the-art mechanically bent timber products, but are manufactured in a more sustainable way. So such as a self-shaped bell CLT for roof structure, which you can see on the left, or maybe also for curved walls in buildings to provide more lateral stiffness, which can also be seen in some architectural projects already nowadays, right? But I think our main focus at the Institute currently lies on performative building systems, as well as fabrication and assembly methods for multi-story timber buildings, because this is what we actually really need. So these projects I present to you today are some sort of a niche. I mean, they're really nice, but of course they will not solve the problems I mentioned earlier in my talk. So to conclude, what did we learn and what messages can be taken from my talk? First, we have to build for more with less. So we have to build sustainable, build with the least material we can, maybe also integrate the most we can in our building components. Also, we need to rethink construction, build reusable, recyclable, and also reconfigurable. And we as a construction industry need to extend integrative design and fabrication methods to construction, making building processes much more efficient. And yeah, also, in my opinion, we should build with more timber if possible. Okay, so this was my talk. I hope you liked it. Oh, and there are much more questions now, I just saw, but maybe we can open up the discussion now.
Thank you. Thank you for that presentation. Yeah, you maybe you can read the questions maybe, so the online student can hear us.
Okay, so I will just start up with Hanni's. I hope if I'm mispronouncing some names, I'm really sorry. Yeah. I start with the first question. So joints are the most important part of every design. In this case, I wanted to know how you design the joints. what was the parameters for you in designing the joints? Okay, it's a really good question, especially since I also in my research concentrate on joints for segmented timber shells and also for something like the tower. So for the Buga, I mean, maybe Hani, if you want, we can also have a dialogue together if you want. So for the Buga wood pavilion, we try to have an integrated joint design with the finger joints. I mean, we used this before, and this has been used in several other projects around the world also before, but have something that is very integrated that you then can incorporate in the component itself. And for the bolt was mainly the decision by the Bundesgartenschau. I mean, it was our decision, our design, but our task was to have the structure be reassemblable, or should be able to be reassemblable. Reassemblable is a word, I don't know. in the end, so to be able just to disassemble again and maybe build it up somewhere else. So that's why we chose this bolted connection instead of something that could not be assembled again. So for the Buga, this bolted connection was the solution. It actually developed in a research project that was done by the ICD and ITD, where I also was involved a couple of years ago, where we came up with this solution. I mean, it's nothing very innovative, but it just, our main design driver was to have it, to have the structure being able to be reassembled somewhere else. So it also will be used in the future, I think, for the next Bundesgartenschau. So these Bundesgartenshows, these gardening shows, they come every 4 years, I think. I'm not quite, or So it will be it will be disassembled, the Buga wood pavilion, and will be reassembled at the next Bundesgartenschau, what I know of currently. So this was the main design driver. And for this, which you can see here on the screen now, for the arches, like where the angle is very steep, the bolts just did not fit. So we could not, the angles were too steep to have the bolts in these positions. And for the tower, it was something else. The tower, you can see it in the model that the seams are very curved, right? And also the components don't always join in the same angle. So there was like this continuous change of angle, and we had to have a very adaptive joint, like a very adaptive joint strategy. And screws are quite nice here. I mean, we thought about other solutions also, but screws are quite nice because you have only one penetration vector, like one linear vector where you can change the angle. But it was also tricky to really fit the connections here, because in the code you have constraints what the distances, like the edge distances of the screws to the timber have to be and all that. So you have to really, actually we had to have this in a parametric model to make sure that all the distances are kept, all the angles are kept, and so on. Yeah. So we thought about other connections, like along the process, also like some integrated connection, maybe with some finger joints, or to mainly transfer the in-plane shear that is happening here along the seams. But in the end, it was just not feasible. So we only went with this screw joint, but which was nice because it was quite simple in a way. So we only had, I think we had every 30 centimeters, we had one pair of crossing screws, and above the openings, like here, I don't know if you can see that, like above the two openings where the force, the stresses were a little larger, we had them denser because we needed, because there the stiffness was not kept. But in all the other parts, there were 30 centimeters. Yeah. So
Okay. Thank
I don't know
you.
if I answered your question, but yeah.
Yeah, just thank you.
Okay. No problem. So there's another question. What type of continuity is achieved with the cross-screw connections? Pinned, okay. How did you model this in your FE analysis? Okay. So Ben, so yes, I mean, if you place the screws in a continuously, you also arrive or achieve a very continuous joint. So it's more like a linear joint, but it's not bending resistant. So it's actually, I mean, you can achieve some bending resistance if you, so there's a truss model I can also, or a paper that was done by Armin Lee. It's just that these crossing screws are actually, they form this sort of truss. So you have some sort of tension stiffness or tension resistance and some out of plane resistance due to this truss model that these crossing screws build. And if you consider that they can take tension in their axis and have some lever arm to the outer edge, you can also achieve some little bending stiffness, but only very little. And if you want to be really conservative, it's actually a hinged connection. And how did we include this in our FE analysis? So for both the Buga and the Tower, we had, so we calculate most, the software that we use is Sophistic, but it's, I mean, basically it's just an FE model. We have all this parameters set up in Grasshopper and Rhino and have actually the FE program just as a solver to analyze the structure and then re-import all the results back into Grasshopper. And we modeled it with a spring connection. So we had 3 linear springs, so one for tension, one for out of plane shear, one for in plane shear. The values for these spring stiffnesses and for these resistances we derived from the code, like from the building code. And then we had one bending, rotational spring, which was, which simulated the bending resistance for around it. But this was very little compared to the other resistances. I think we also published some papers if you really want to dig into that for the ISS. I can also provide later, maybe provide the papers where you can read about this more extensively. Or So I hope I answered this question. Okay, the next is from Sanas. I am wondering to know about your solution for the protecting the panels against swelling, and all reaction may happen due to the rainfall and climate condition like contraction, expansion. And how do you make sure that there is no water penetration through the panels? Okay, yeah, this is also a really good question. So for Buga, we had actually these, I think they were CNC cut EPDM foil that also hexagonal form or the same form or same shape as the components, but they were overlapping the always two components. So we made sure that that the water would never penetrate this foil and would never touch the timber, but only on the top. And for the tower, it was pretty much the same. We had the structure itself, the structural part, the CLT panels. Then we had this sort of a different foil, but also I think was also based on EPDM, which could be removed or can be removed afterwards. It was not glued onto the surface. It was actually stapled, I think, to the surface. And then a large facade to have this, of course, the timber timber look again. And for the tower, I mean, you can see here it was actually, so this was a concrete foundation, and the tower was actually it sat on these steel brackets, and we just made sure that whenever rain is kind of, we also did some rain analysis, but whenever rain is or the water is running down, that it never gets stuck here. So we had to put in some openings in the brackets and just made sure that all the rain always, or the water can always, will never, or that the structure will never sit in the water anywhere. So if it gets wet, it's fine. You just need to make sure that it dries again also. So this is quite important. But I can also try, or is someone talking, speaking?
Thank you.
Yes, is that enough, or is so we?
Yes.
Okay, just we needed to make sure that the structure doesn't sit in water, and Also, the roof was actually overarching the structure so that the rain would not go into the structure inside, but trip on the outside where the large facade and the EPDM was, and then just trip off here on the edge. But of course, sometimes, yeah, these edges like on the openings do get wet, but they just have to, you just have to make sure that they also can dry again, so they never. But if possible, you need to protect the structure from water as good as possible. Like, yeah, as good as possible. Yeah. But I think there are also some detailed photos online. If you, I think so. Maybe I don't know if I for Buga if I have.
Thank you.
One, but yeah, I hope I answered your question here. Just gonna see if I mean, yeah, you can. Well, my computer's stuck. Yeah, I don't know. I think my presentation. Yeah, but no, sorry. You can see it here. I think that there's like these EPDM. I mean, we always protected during the assembly of the Buga. We always protected, or the company, not us, but the company who assembled it, always protected the timber from getting wet, because it took a few days, right? So, and it was raining during the time. So, but there's this EPDM. I don't know if, yeah, it's probably, there's no photo where you can see it. I'm sorry, but.
No, it's okay. I can understand.
Okay.
I got my answer. Yes. Okay. Thank you.
Yeah, you're welcome. So Mahmoud posted a question on the tower project. Are all external surface curvatures simply trimmed from a cylinder surface? Yes. So this is what I showed here, right? So I mean, just maybe to explain this again. So we designed with this cylinder. Yeah, using the cylinder rotating around these two control circles on top and bottom. And then it was just a simple intersection and trimming of the surfaces. And then these surfaces remain. So the tower components are only single curved, right? They're not double curved. They just kind of seems like they're double curved, but they're only curved in this direction. So I don't know. So in this direction. So this is actually all a developable surface. So, and then similar cylinders were then used for fabrication. So we used these kind of fabrication blanks and cut off the tower components from these cylinders. I think you can also see it a little further. Yeah, here, I mean, the cylinder is not there anymore, but we try to nest as many components on one half cylinder blank as possible. And here, so they're only single curved. I don't know if you can see my mouse, but they're only curved in this direction. So like this, and the rest is like the other. Yeah, so it's a developable surface, right? And these are then the cutoffs. So here, the cylinder was lying on the left here on these kind of, yeah, on these little walls, like these kind of half cylinder walls, right? And where we cut off the component. So this is not the final component, but here on the right, you see the final component.
Okay, great. So the self-shaping technology was used to achieve a single curve shape at the end surface, right?
Yeah, exactly. And so I think this, where do I have it? Yeah, I think here you can see it quite well. So the pieces are actually smaller, so they're not. It's not like this entire cylinder self-shapes, right, into one large half cylinder. It's actually that you have these, what you can see in the middle. Can you see it? Is the video running?
Yeah. No.
So you have smaller parts. I think they were like, I mean, a little larger than this one, but I don't know the exact dimensions, but it was something like a meter by, I think a meter by, I don't know, the length was quite long, but the width was a meter, and then they were we dried them in the kiln, and then they self-shaped, and then afterwards they were added together, laminated again together. Yeah. So.
But you were able to achieve the exact radii of the cylinder with self-shaping technology, right?
I think it was within 5 to 8% accuracy in the end. Yeah,
Okay.
but this work is really this is not my work. I mean, I find it fascinating, but this was done by the ETH in Zurich and by the ICD. So it is a collaborative research project by the by the EMPA actually of the ETH. So by the two institutes, and yeah, I think it's been going on for a couple of years, and they tested different wood species, tested different moisture content. So it was a really like there's also a paper in. I can also share this paper. What is it? Where's it from? Let me check. But I can send it also later.
Yeah, that would be cool.
In Science Advances, there's like a really elaborate paper on this self-shaping. Yeah, but this is how it was done. And like on the left here on the screen, you can see how large the components. I don't know if this was actually, if this was the first test specimen. I think so. This was not then the final like half blank or half cylinder blank. But yeah, that's basically what it looked like in the end.
Okay, great, thanks.
Yeah, of course. Okay, what software do you recommend for analyzing the impact of wood-wood connections, like the finger joints and the bugs? The Buga shell and the structural behavior of the structure from Fasane. I hope I pronounced this correctly. Yeah, so I mean, there are a lot of different softwares out there, right? What we basically do, like I mentioned earlier, is that our models are usually set up in Rhino and Grasshopper, and then one of our colleagues, he wrote a plugin that kind of links with Sophistic. So you have all of, like we mainly work in Grasshopper and use just an external FE software. It could be any kind of software. I mean, we just use Sophistic because it's quite handy in that sense. Yeah, where Sophistic is just a solver to calculate or analyze the structure, and then we re-import the results that we need or that we want to have back into Grasshopper, and all the design checks and all the connection checks, for example, or the stress checks we then do in Grasshopper again by also, I mean, writing, like using this plugin and also writing own programs to do the simple design checks. So for connection, for example, after the model is analyzed, we get the forces in the connections, like from our string model, yeah, and then we re-import these forces into Grasshopper, and then there we compare them to the resistances of the connection that we gather from the codes. So it's in some sense quite simple. It's just that we want to stay in like a parametric environment to be able to, if we have to change something about the design, that we can also do this very intuitively and also very integrated. So, but we use, sorry, yeah.
Thank you.
Yeah, does this answer your question?
Yes.
But
yes.
you could, there are also far better, of course, FE programs to analyze timber structures. Like one which is quite common here in Europe, I think, is RFEM, like from the company Tluval. But I mean, around the world, there are, of course, many others. Like, but they, like RFEM, for example, has like also built-in design checks for timber structures.
Okay.
But we used Sophistic. Yeah, but basically you can use any FE solver. You could also write your own FE solver if you feel like it. The design checks in the end we did by the code and wrote our own small program for either for stresses or for connection checks maybe. So I have a. Let me just show you quickly something where this is a little bit better illustrated. Wait, if you give me a second, I can show you. I hope I'm not over using my time.
All right.
So this was a presentation about Buga I've done for the ISS in Barcelona. And I think, I mean, can you see, you've seen it, but this is what I wanted to show you. So maybe this explains it quite well. So we have, I mean, on the left, I don't know if I showed it, no, I didn't. We have the architectural concept, and then we have our parametric model, which is like our geometric design segmentation. And also it is linked to fabrication. So what is actually possible to fabricate. And then for the structural part, we have this pre-processing where we within Grasshopper define all the pre-processing steps. So we apply a material, boundary conditions, connection details using kind of these spring models. I mean, it's very generic, I know, like the little logos, and we apply loads. Okay, so this is all happening. Do you see my mouse actually?
Yes.
Yeah, okay. So this is all done in Grasshopper, and then we use Sophistic. So this is the logo of Sophistic. Use the Sophistic, but it could be any FE program as an external solver. And then from the Sophistics data bank, we re-import our results in a post-processing step into Grasshopper, and then do the design checks in Grasshopper. So I hope this somehow, and this, I mean, these little green brackets here should highlight that it's all done in Grasshopper. And then if everything is all right, we can then construct the shell. I mean, of course, there are multiple other steps in between, but yeah, that's how it. Maybe maybe I should have shown more structural part. Maybe if we already added, I can. So this is how we did it for the Buga. So here you can see 3 cassettes. So the way we modeled it, we had one compressive, or we modeled the components with surface elements. So they were all with shell elements that had a certain thickness. So also the top plate, the beam, and the bottom plate were all modeled with shell elements. And here in this section, you can see the connection. So for the top shell element, so the red lines are actually the shell elements that you can see here. I mean, or how it was implemented. So these are our shell elements with a certain thickness, right? So the top shell elements, they had this compressive spring that only could work in compression, like if there was contact between, like if you bent 2 components, that there was contact within the 2 top plates, and the same for the bottom plate. And for the bolt, we had a tensile spring and an in-plane and out-of-plane shear spring. So there was, the bolt can actually take in-plane. So if the 2 components want to deform like this, or they want to deform like this, you have some resistance. And by having a top, or like a compressive spring on the top and the bottom, and a tensile spring in the center, you have some sort of inherent bending resistance, right? You can imagine if it then tries to bend, it compresses out the bottom, but with a lever arm only from, of course, from the bolt to the top or bottom layer. Yeah, maybe I should have shown this. Sorry, I forgot.
Thank you.
Okay. But if you have further questions, of course, we can talk about this more. So next question. Hello, dear Simon. Thank you for your good presentation. Thank you. Exploitation of timbers as a surface active structure is very good and intelligent, but after the shrinkage, how did you form it into a double curvature? Okay. So I guess this is regarding the tower. Just controlled it with heat and material research and shrinkage properties. So Ali Reza, so I mean, as I mentioned before, and what is, a lot of people ask us this, if this is double curved or single curved. So this is single curved. I mean, I explained it before. I don't know if should I explain it again, but so we controlled it by the self-shaping process, what Mahmoud already asked. And afterwards, of course, timber always shrinks and extracts or expands, right? But the way we did it, and the way it is done in industry, you dry it to a certain moisture content that is usually also what you have in your like environment, and then the shrinkage and swelling is not as as large as like that you kind of you prevent it from shrinking and swelling it too much. So you try to a certain moisture so yeah, we were actually quite happy that the drying for the self-shaping was like the final moisture content was pretty close to the one that you have in your environment. So then after, once you have it dried, it doesn't shrink and swell that much. But it still, of course, works, right? The timber always, somehow works or has some natural movement. And this we also implemented some sensors to actually survey this. Yeah, so I hope this was answered. If not, you can also ask more. So Sita says, fantastic work, thank you. Just wonder for the tower how to simulate the drying shrinking process using computational design tools, as tiny errors may lead to material waste, especially in this case. Yeah, that's true. Once again, this work was not done by me. So this was done by the ETH and the ICD, right? But the way they did it, they did it in a volumetric FE model, so not what we mainly use for our global structures, but it's a more detailed analysis. I mean, I'm sure you're aware of this. I think they did it in Abacus, and they simulated it here to where you have like a 22% wood moisture content, and then they let it dry in the simulation to 12% and see how it then deforms. So this research, I think, probably also it's better for you get more insight if you read the paper. I can share it later in Science Advances, because there they explain it quite elaborately, I would say. But that's how what I know of is how they done it. So they simulated this and then also tested it with physical prototypes. And I think I'm not sure if it's actually done in a parametric environment. It probably could be, or it could also be parametric in Abacus. Did I answer this question? Hope so. So it's actually, every timber part has some sort of wood moisture content. It's about drying the timber, which has to be done anyways. Like in every industrialized process, you dry your wood, and using this drying, like these are the drying chamber on the very top right, or this very large drying chamber where the parts are there. By drying the components, they actually formed, right? So you have like one layer that is like where the fibers are lined perpendicular to the length of the board, so it dries. So yeah, timber has a different shrinkage and swelling characteristics or properties in different fiber directions, right? So by having one perpendicular to the other, you kind of induce this curvature. I hope this is somehow understandable. So you also work with the fiber orientations of the boards. And then in the end, I think they added one locking layer to not have it go back into its flat state again. So you add another layer to lock it from going back into a flat state again. I hope this answers your question. Okay. Ben also said, thanks, could you send the papers? Of course. I try to send you all of them, the ones I talked about. Okay. I didn't follow the chat. Sorry. I got it in Mahmoud's question. Okay. All right. So I think that's it. I don't know if there are any further questions. Of course, you can ask me more. If not,
actually, even if you don't mind, we still have some questions online from the auditing students.
Okay.
Maybe I will read them, and I will also paste them in the chat window so you can see them.
Okay. Yeah, sure.
Okay, so first one from Thanos, why are the edge arcs wavy? It's I think it's comes when you are presenting the Buga.
The Buga. Yes. So I guess you talk about this, like that you have these kinks, or is it that what does wavy mean? Or is it because it's kind of, it's not like a perfect arch? Maybe it is that. So this is a design intent actually. So what maybe this is, yeah, this is what Thanos meant. So it is, you have to know that we did some form finding on the shell, but it's not a purely form found geometry. So it is a trade-off between architectural design intent and yeah, and structural optimization, structural form finding. So it's something in between. So we did many different, I can also show you here, we did many iterations here, where we tested different parameters, like the wing angle, the S-curve, which was also one very significant design feature of the shell. So we tested different geometries, analyzed them structurally, once on a continuous shell, like a monolithic shell, and once on a segmented shell. And we just checked how good they perform, and where there could be a trade-off between like architectural design intent and structural optimization, structural form finding. So it is not a purely form found geometry. We didn't want that, so we wanted to wanted to be somewhat expressive also in a way. And yeah, so it was this kind of trade-off, and that's why it actually has this kind of wavy shape. It's intended to have these arches, or that the arches have these shape. And Sadra, thank you for the presentation. Yeah, you're welcome, of course. First question is, how can we control the amount of curvature of the timber by self-shaping? Is it the amount of moisture? Yeah, I'm also not the expert here. Sorry for that. It is about the amount of moisture, and also about, I think about the thickness of material and how they are aligned. So if you align them perpendicular to another, you can achieve more curvature. If you align the fiber orientations differently, other curvatures you will achieve other curvatures. And in my, for my talks with my colleagues, I know that you can control this quite accurately now, or they can, at least. But it's quite, yeah, you can control it quite accurately, and you can reach actually quite some differences in curvature. And it is, yes, it is due to the moisture content. So if you don't dry it as much, like a different curvature will, it will end up with a different curvature. But I think, yeah, the more like they also, I'm quite sure I read it, but they talk about their paper, about this in their paper in Science Advances. But for that, you could also reach out to Dylan Wood from the ICD, which was part of the research project on this, about this topic. Maybe he can answer your questions here much better. He also has a TED Talk soon for TEDx Stuttgart. So where we live, there's a local TED Talk, and he will, I'm not sure if he will go into that much detail, but if you want to check it out, I think it's in September, a TED Talk about the self-shaping process of the tower. So maybe just look out for that, and the paper, of course, is or the different papers that we published are also very helping much on that. Yeah. Okay. Are there more questions or?
Yes, it's a follow-up question by Sandra.
Mm-hmm.
The second question.
Okay. Yeah. So shall I read it, or? I have to read it anyways, right? So by the change of the climate, do the timber revert to previous state? For example, by changing the moisture or raining days, how would you control? Yeah, this is what I meant by the locking layer. So maybe go back to the other presentation. I don't know if you can actually see the locking layer there, but just enlarge this. So there's an active layer and this kind of passive layer, and once it is formed, here, then so once it's self-shaped, you add a locking layer which is cold bent. So you bend it, a very thin layer, you bend it over and laminate it to the timber, and this prevents the entire piece from deforming again. So it would, even though if the moisture content changes on the outside, it will not go back into a flat state or into a different curvature. At least not to a certain extent. It will, I mean, of course, moisture always affects wood and always changes or it tries to change shape, like the change in moisture content, but it will not, it will be very little. Okay, Nada has another, I hope this answered your question. Nada has another question. Thank you very much for this amazing link. Thank you. I have a question about the Urbach Tower. What about its base to make the tower is stable with its height? Okay, yeah, so yeah,
I think we have another question with a similar.
Okay, also to show and explain the foundation of both projects. Okay, yeah, okay, so for the tower, I mean, I can show it in the model, or I can also show it. I think there was one slide where we have more detailed. No, it's not here. Wait, let me open up another presentation. Sorry. So for the ISS, same in Barcelona, like for the Buga, I also did one presentation for the tower. And the one I presented today was kind of a mix of the two, right? I mean, as you figure. And I think I have, and you of course see very similar slides here when I'm looking. Is it here? Ah, yeah, okay. So this one. So this is kind of like an overview of the tower design. So that's what I mean, for the foundation, you can see is kind of this concrete foundation. So this was also an architectural design intent to have the tower elevated. It's not, I mean, it also helped for kind of rainwater to be drained off properly. But it also, of course, meant that we had to an additional effort kind of for these kind of steel brackets. If you look at my mouse that you see here, so the tower was actually kind of standing on these steel brackets, and the steel brackets were actually hanging onto the foundation. If this was due to a lot of decisions during the project, because we had first at the very beginning we had a different site where the tower was supposed to be erected, but this changed, and then for this new site we wanted to have it to be a little elevated, and so we decided as a design intent to have it kind of on a concrete foundation. Sorry, my voice is on this concrete foundation. Yeah, for that, of course, we also did some checks. So for the global structure, you have like wind loads that are mainly like the kind of the dominant loads for this tower, right? And so the tower tries to rotate, and then you have some bending moments and some, of course, lateral forces and also vertical forces that have to be taken by the concrete foundations, right? So we did a global simulation for the tower and had it with a hinged support, and had it supported on it where the brackets are, and then from these the resulting forces we calculated the foundation. So this, I mean, it's pretty straightforward. We didn't have the foundation in the, I mean, we had it in the geometrical model, but not in the structural model per se. So this was done in an additional step. So what we did, we took the support forces, or the resulting support forces, and applied it in another analysis onto the foundations. So, I mean, just to simplify the model, because you could have done it also probably all in one model, but sometimes it's better to have separate models that are just simpler and cleaner than trying to implement everything into one model. It is nicer than only have one model, of course, but it also, you have to make sure that everything is properly connected, is properly simulated, and this makes it sometimes a little bit, more difficult and also not so straightforward, and also computationally heavy, right? So that's how we done it for the tower. And for the Buga, there were also these like there was 3 supports, right? 3 large supports, and there were also some linear concrete supports, and they were also the cassettes. I don't know if you can. I don't know if let me see if I find a picture real quick or an image where you can see that. Okay, this. Yeah, this is a little. It's not the best picture. Ah, yeah, this is one. So this is how it was done. So we had these steel brackets that were also part of the geometric model, where we used the same connection for the to connect to the wood components, right, by a bolted connection. So this is how it was done. And then these steel brackets or these steel parts, they were then welded to an embedded steel part that was connected to concrete. But here, what was quite difficult, because we work with a different engineering company, because they took care of the calculations for the foundations, and it was a little bit like they proposed some solution, and we thought, I don't know, it was a long discussion, but we ended up with something like this. Yeah, so these parts are. These were like, I think, around 30 individual parts, but we had a parametric model where we could change them quite vividly, and then also extract all the plans to produce them very quickly. So if the global design of the shell changed, we could also then directly change these parts. This was quite helpful for that. But that's how it was supported. And here on the bottom, you just have like a normal concrete support, and of course some drainage for the water, because the water runs off here. Okay, I hope this answered your question.
We have a last question.
Okay.
I know.
Okay. Okay. Amazing projects. Thank you. Thank you for showing us regarding the Urbach Tower. What's happened to the material remaining from the cylinders cut? Okay. Has it been reused somehow in the project or somewhere else? Unfortunately not. Yeah, I mean, this was really cut off. This is something, of course, for the future, which could be changed, I would say, or could be improved maybe. You always, I mean, in timber construction, you always have cutoffs. That's just normal and just not avoidable, I would say. But it was not used. But for maybe one example, just to show how it actually could be, how it was done in the previous project for the Landesgartenschau shell. This one. So the one that was done in 2014, the cutoffs were used for the floor, like for the 50% of the cutoffs of the components up here were used to then create the floor. So this is a way to actually use the cutoffs better. Or you could, what I also saw, like I think Christopher Robello from, I don't remember where he is right now. He's a professor now. I think he also does segmented shells, and he tries to sometimes use cut-off material from normal timber construction and then use this cut-off material and create other structures. So maybe if we have enough surface area or enough material left, you could use it for another structure, or use it for something that within your structure, right? Like the floor here in this example. That is maybe something that would make sense. But Of course, this is a really important aspect because, I mean, if you cut off 50% of the entire material and it's just waste, it's not so nice, right? But I also have to say, of course, this tower is a very, like, kind of, in that sense, yeah, not unique, but it's so kind of, in the sense, special that it's not really, you could, I mean, what I proposed here also later, if you just use the kind of these barrels for just the roof, then you don't really have any cutoffs, right? So the components for towers were quite special. And so it's, yeah, it's quite straightforward that you have then also quite some cutoff. But if you did like a roof, like this kind of this barrel roof structure, then you could use the material much more efficiently, I would say.
Great.
Okay.
So if there's no more questions, maybe we have already so we don't imagine this lecture and the Q&A section will last for so long. And actually, it's already the time for a break.
Okay, yeah, sorry for keeping you, maybe it was too long, I'm not sure, but I hope you liked it.
Yeah, really, thank you again for the very exciting projects and the informative lectures. And also big thanks for your time.
Yeah, of course, I'm really honored. It was much great fun. I mean, I really thank you for having me, and I will just forward the paper either in the chat here or I will forward them to Jakob, and then he can share it with you guys. The paper I talked about. I mean, I shouldn't forget.
Okay, so maybe we'll thanks Simon again, and we will have a break, and we will meet you all. What was 20 minutes later? Half an hour? Yeah, then yeah, okay, so just half an hour and 11. It will be 10, 11. I don't know. It's how to say? Yeah. So we'll have the break and meet you later.
Okay. Yeah, you're welcome. Thank you. Bye.
Bye. Yes, and it's really awkward.
Yeah, 10 past 11, 11:10.
Okay.
Both